Welcome to the Introduction to Chemical Reactor Design module, a part of the Catalyzed Transitions to Chemical Engineering course. In this module, over the next few lectures, we'll be talking about chemical reaction engineering, why it's important, and some of the fundamental concepts that we learn in this course. This course is important, and how it fits in with the rest of the chemical engineering curriculum and discipline is easy to see if we think about what it is that chemical engineers do in principle. And in general, what we do is take raw materials and convert them through various steps into more valuable products. And one of the things that separates chemical engineers from other types of engineers is that we, at some point in that process, inevitably use chemical reactions and transformations in that conversion. So in this course, we'll be drawing on some of the different areas that you've already been focusing on in the Catalyzed Transitions curriculum, like thermodynamics, fluid mechanics, heat and mass transfer, and so on. Trying to put that together in order to understand how we can engineer chemical reactions as well as design chemical reactors. When we talk about designing a chemical reactor, typically what we're talking about is choosing the right type of reactor. We'll be talking about 3 or 4 main types of reactors, and then figuring out how big it needs to be. So how large, what volume does it need to be, which, as you might expect, is going to impact the cost. Because the bottom line, what we're trying to do is to maximize the space-time yield of our product. We want to make as much product as we can in the shortest amount of time using the smallest reactor vessel possible, i.e. the cheapest reactor. And so in order to do this, how quickly or well the reaction proceeds, it's going to depend on a number of factors, including stoichiometry, kinetics, mole balances, and fluid dynamics. We'll be talking about each of these and how they affect our reactor design process. So you're no doubt familiar with chemical reactions from taking multiple chemistry courses. And when we're just talking about a chemical reaction in those courses, we're typically focused on the molecular phenomena, thinking a lot less about the environment that the reaction's taking place in. So it's more of an idealized flask, for example. And there, of course, stoichiometry is important, the kinetics, and whether we have just the one or multiple reactions. Those are all important considerations. But as we move towards reactor design, the environment becomes much more complex, and there are many other factors that we have to account for. For example, as things get larger, it can be harder to maintain the temperature. So is our process isothermal or non-isothermal? Mixing can be more difficult, which can introduce non-idealities. So do we have an ideal or non-ideal process? And then some processes will be inherently steady state, like continuous flow processes, and some will be inherently non-steady state. So knowing the difference is going to be very important. So as we start to learn more about the pros and cons of different types of reactors, we'll be able to then also decide what reactor is best for the job. The 3 main types that we'll be focusing on in this module will be the batch reactor, the continuous stirred tank reactor, or CSTR, and the plug flow reactor, or PFR. Okay, so let's get started. And in this course, we'll be following along with the Fogler textbook, Elements of Chemical Reaction Engineering, not touching on every chapter, but several chapters of the key chapters, as will be indicated in the slide set. So in chapter 1, we'll be focusing on mole balances. And when we're talking about a chemical reaction, whether we know a chemical reaction has taken place, the way we're going to define that is by saying that occurs when a species has lost its chemical identity. So what is an identity? Well, identity is determined by the kind, number, and configuration of a species' atoms. If it has more carbon atoms than one molecule than another, okay, that's going to be a different species. We'll have a different identity. And so there are 3 main ways that a species can lose its identity. It can decompose. So C could go to A plus B, something breaking down, for example. It can combine with another chemical. A plus B goes to C. Or it can undergo an isomerization. So the molecular formula stays the same, but the structure changes. Whatever type of chemical reaction we have, that will be occurring at a certain rate. And for us, we'll define the rate of reaction as the rate at which a species loses its chemical identity per unit volume. So it can be the number of moles disappearing for one of our substrates, okay, or it can be the number of moles appearing for one of our products. And so we're going to talk about reaction rate in two different ways, depending on which of the species we're talking about, our reactants or our products. So it could either be the rate of disappearance or consumption of a reactant. We'll denote that as negative R, in this case, negative RA, or the rate of generation or formation of our product. And that would be positive R, in this case, positive R sub B, for the reaction going from A to B. Now, the difference might seem subtle, but it is important to keep track of this negative sign, as that's going to help determine whether something is disappearing or appearing, forming in our mass balances. Now, chemical reaction rates are always, for a homogeneous system, written as a per volume. And why is that important? And that's because reaction rates are going to be highly dependent on concentration. Okay, so we can see in our units, the reaction rate has units of moles per meter cubed per second. What moles per meter cubed? That's a concentration unit. So let's look at this example where we have a reaction of A plus B going to C. If we have three molecules of A and three molecules of B, we can see that as the volume gets larger, our molecules are further apart. Okay, their concentration is lower, the volume's gotten larger, the term in the denominator has gotten larger. If our molecules are further apart, it'll be less likely that they'll be colliding, or they'll be colliding at a smaller frequency. So they'll be proceeding, the reaction will be proceeding at a slower rate. So our reaction rate is going to depend on concentration. It's also going to depend on other factors, including temperature, pressure, and catalyst, if we are using a catalyst. Typically, we'll write our reaction rate in terms of a rate law, where it's directly proportional to concentration by some order. Okay, in this case, if it's a first order reaction, our rate of reaction is equal to KCA, concentration of A. Or if it's a second order reaction, it'd be equal to KCA squared. Okay, and so on. In both cases, K is our rate constant, and our rate constant is a function of temperature, as we can write according to our Arrhenius equation. Okay, so it's going to depend on our pre-exponential factor, the ideal gas constant, most importantly, the activation energy, and then the temperature of the reaction. A few more notes on rate laws. These are algebraic expressions. The reaction rate almost never remains constant throughout a chemical reaction. It's usually changing as a function of time or sometimes space within the reactor. These are relationships that we must determine experimentally. So we'll talk about how we will do that a little bit later in the course. And these are relationships that are not affected by what type of reactor we use. Okay, they'll depend on the temperature, they'll depend on those other environmental parameters, but not the type of reaction. They're independent of that. One of the main tools that we'll be using in chemical reaction engineering are general balances. Specifically, we'll be doing a lot of mole or mass balances, and then later, as well as energy balances. But in general, balances are physical laws that state that mass, energy, and momentum are conserved in any isolated system. So mass cannot be created or destroyed. It can only change states, for example. The same would go for energy. So if we think about an isolated system as we've depicted here, we can have material X flowing in. We can have material X flowing out. It may be generated inside the system. It may be consumed inside the system. But the balance of those, whichever terms are involved, would then be equal to how much is accumulating within the system. And so to put that into context for a chemical reaction process, where we have a system with a volume V, where we may have, for example, our reactants flowing in, being reacted in the volume, and then leftover reactants flowing out, we could write a general mole balance for some species J that would say the rate of flow of J into the system, which we could also denote as Fj naught, the flow in, is equal to, or sorry, minus the rate of flow of J out of the system, Fj, what's leaving, plus the sum of the rate of the generation of J by a chemical reaction minus the rate of consumption of J. Sometimes we'll have both terms, sometimes just one, sometimes the other. The net effect of that we'll call G sub J, our generation term. Those differences is equal to the rate of accumulation, where N is the total moles of J in the system at any time, and that can be changing with time. And so the way we'll typically talk about this in short terms is in minus out plus generation minus consumption is equal to accumulation. So that's a good shortcut to remember. Now, if our system is spatially uniform, then the rate of generation of J is equal to the rate of reaction of J times the volume of the reactor. Now, that's not always the case. Sometimes our system volume may not be spatially uniform. In this case, if the rate of reaction of J varies with position, then we can consider the total volume as a set of subvolumes, where in each of them there will be a unique reaction rate. So the rate of generation of J in reactor volume 1 is equal to the rate of reaction of J times that volume, that subvolume. Okay, and likewise for 2, and for 3 and 4, and however many, up to infinity, for example. If we divide this up into a set of infinite, infinitesimally small subvolumes, then in the limit, okay, we can sum all of those contributions to the overall rate of generation together. Okay, in other words, we can integrate the rate of reaction of J over volume and get the total generation term. So to summarize that, again, we can describe our system, general mole balance, as in minus out plus generation equals accumulation. We have our rate of flow of our reactant species in, less the rate flowing out, plus the rate at which it's generated, is equal to the rate of accumulation. If we have a uniform volume, we can replace our rate of generation with the rate of reaction times the volume. If our volume is not uniform, okay, i.e. in a non-well-mixed system, then we can integrate over the volume to capture all the individual contributions throughout the volume. These will be known as our general mole balances. And in different types of reactor systems, we may or may not have all of these terms. For example, we may not have flow in or flow out. We may not have accumulation if it's a steady state system. But this will be our starting point that we can use, and then from here, make assumptions and apply it to each of the different individual types of reactors that we'll be discussing. So the first type of reactor that we'll be talking about um, and developing design equations for is the batch reactor. Okay, it's possibly the reactor you're most familiar with in your chemistry classes when you were doing reactions in a beaker, for example. That's another way to think of a batch reactor. Of course, when we scale these up, they look a bit more sophisticated, um, especially with respect to mixing and so on. We use them a lot, especially in small scale applications to test out new reactions, as well as to characterize reaction kinetics, as we'll see later. The pros of a batch reactor is that you can typically achieve high conversion. You just keep the contents in the reactor longer, and they're relatively easy to do. Um, Mix our substrates together, we mix, we heat to the right temperature, and so on, and let the reaction proceed. The cons, they can be labor intensive because after each reaction, we need to stop and clean and restart. They're a bit time consuming, especially if we want to achieve high conversion. Our reaction rates will slow down as a function of time, and so we can wait a long time for the reaction to complete. And lastly, there can be some variability from batch to batch. So how do we run them? We mix together our reactant or reactants in the reactor and then allow the reaction to proceed for some amount of time. How long depends on the conversion that we want to achieve. Otherwise, these are a closed system. We're typically not adding any other reactants or products during the reaction. That only occurs at the end. Because as reactants are being consumed, products being made, these are happening over time. A batch reactor is inherently operates in an unsteady state manner. In our case, we'll be talking first and foremost about ideal batch reactors. In this case, we'll be assuming that the vessel is perfectly mixed. This means that concentration and temperature will be spatially constant. However, because we're operating in under unsteady state conditions, they will be changing with time. So now that we know how a batch reactor is operated, we can return to our general mole balance equation for the batch reactor and start to simplify it for the case of a batch reactor design. So since we have just contents being added at the beginning and only taking out at the end at any given time, there's no flow in, there's no flow out, so we can eliminate these terms. So we then have our rate of generation is equal to our rate of accumulation. We can simplify that further. We get our batch reactor design equation. This is our general equation. If we can say that a reactor is spatially uniform, and then we can simplify our integral here and write that the rate of change of moles of J over time is equal to the rate of reaction of J times the volume. So this would be we would call the ideal batch reactor design equation. The next major type of reactor that we'll be talking about is a continuous stirred tank reactor, the CSTR. This operates differently than a batch reactor, although the vessel sometimes can look the same. However, in this case, we'll be continuously adding reactants and continuously removing products as they're made. Okay, so our inlet streams will come in and mix in the reactor instantaneously, and products will be coming off the bottom. The hallmarks of a CSTR is that they operate under steady state conditions, which means that the reaction rate does not change with time. And we'll be assuming, typically in this course, that we have an ideal CSTR, meaning that the vessel is perfectly mixed. So those two together mean that concentration and temperature are also spatially constant. Another implication of the CSTR is that the composition in the exit stream leaving the reactor is the same as that inside the reactor. And if it's well mixed, it'd be the same at any point inside of the reactor. So some of the pros and cons of a CSTR. The main advantage is that they allow for continuous operation because we'll have reactants continuously coming in and products constantly coming out. So these are relatively inexpensive to construct. It's again a batch reactor. We just need to now also have some pumps for our substrates. They're easy to maintain, temperature control because they're operating at steady state, and they're relatively easy to access the internals, I would say, relative to a plug flow reactor, which we'll talk about next. The cons, however, is that mixing then becomes very important, and our reactor contents can bypass and short circuit out of the reactor, as is depicted here, if we're not designing that properly. We can also have dead zones where no mixing is occurring. And another challenge with CSTRs is that conversion is small compared to other flow reactors. And that's due to that fact that our reactors are operating at the exit conditions. The exit concentration, which is typically low, is equal to the concentration throughout the reaction. Since our reaction rates depend on concentration, then so too will be our reaction rates. So now we can apply our general mole balance for the CSTR, again, in minus out plus generation equals accumulation. So we will, in this case, compared to batch, have flow in, we have flow out, as is depicted. We have a reaction taking place, but again, we're operating at steady state, so our accumulation term goes to 0. So with that, then we have our general CSTR design equation, but now if we make the additional assumption that we have our system is well mixed, our concentrations are spatially uniform, we can simplify our generation term as just Rj times V. And then we can rearrange and get the ideal CSTR design equation. And this is written in the case where it solves for volume. So it's telling us how big our reactor would need to be in order to reduce the concentration of our substrate down to a certain level by the time it exits. So this is how large our reactor would need to be to reduce the flow rate, the initial concentration at the inlet to a target at the outlet. Later we'll define this in terms of a conversion. And so the question then is, how do we figure out what is our molar flow rates? Well, those are just our concentration, so our moles of our species J per volume in the inlet stream or in the stream in general, times the flow rate of that stream. Okay, so we can rewrite that in terms of concentrations and flow rates as well. And oftentimes, if it's a liquid system, then our flow rates will be equal from the inlet to the outlet. The third type of reactor that we'll be considering is the plug flow reactor, sometimes called the, a PFR, or sometimes called a tubular reactor. And unlike a batch reactor or a CSTR, it has very simple design, no internal mixing components or other features. It's essentially just a pipe. Our fluid is, our reactants are flowing through it and reacting as they go along the length of the tube of the reactor. Key features of PFRs is they operate under steady state conditions, meaning the reaction rate does not change with time. However, the reaction rate is going to change with concentration since our reactants are consumed as they flow down the length of the pipe. Okay, so the longer they spend in the pipe, i.e. maybe the longer the reactor is, the greater the reaction will happen overall. We can also assume ideal conditions for a PFR. In that case, that means we assume that there's no variation in concentrations radially. Okay, we just have concentration variation axially as the contents move down the reactor. That'll also be true for temperature and therefore also for the reaction rates. So when are the PFR used? Oftentimes we'll use them for gas phase reactions because less mixing is required. And they have several important advantages. First, as was already mentioned, they have no moving parts. There's no stirring, less things to break, lower energy costs that way. Another main one is we can achieve high conversion. So unlike the CSTR, which operates through the outlet conditions, the PFR the concentration is the same throughout each plug. And again, it's just changing as it goes down the length of the reactor. And other advantages, they have a low pressure drop. Cons, temperature can be difficult to control, so it can be changing as you go down the tube, and so you need a proper heat transfer equipment to make sure that you're maintaining, if you want to maintain isothermal conditions throughout. So the key things we need to keep in mind for a plug flow reactor, again, is that the concentration and reaction rate are going to vary axially. Okay, so as the reactions go down, the length of the reactor, but not radially. Okay, not from the center to the wall. And so now if we want to apply our general mole balance for PFRs, in this case, it's helpful to think about a differential volume rather than the entire volume of the reactor. Okay, and that's because our concentration is varying throughout the entire volume. So within a differential volume, we'll assume that the concentration is constant. And so then if we apply our design equations, so in minus out plus generation equals accumulation, we said that the PFR is going to operate at steady state, so there'll be no accumulation term within that differential volume at that time. We can rearrange and then divide by delta V. And ideally, we want these differential volumes to be as small as possible. So if we make that differential volume go to 0, then we see what should look familiar to us as the definition of a derivative, okay, of f with respect to v. Okay, and so we can rewrite that as df j dv is equal to rj. And this is what we would call the ideal PFR design equation. And the last type of reactor that we'll talk about, but not as thoroughly as the other three so far, is the packed bed reactor, the PBR. And this is also a tubular reactor, much like a PFR, but in this case, inside the reactor will be packed together heterogeneous catalyst. So like a solid, for example, maybe it's a heavy metal or something like that. But the catalyst surface is where the reaction will be taking place. And because of that, it's not taking place throughout the entire volume of whatever the fluid is, a liquid or a gas. It's only taking place at the surface, so we will represent our reaction rates not as a function of reactor volume, but as a function of catalyst weight or mass. Like a PFR, we also assume steady state conditions, so the reaction rate concentration does not change with time. So what's good and bad about a PBR? Well, you can achieve high conversion rates due to lots of contact between the catalyst and reactants, and they're generally low-cost reactors again, much like a PFR. There's a tube. The catalyst, of course, can be expensive depending on what you're working with. The cons are similar to the PFR, but there's a couple of different ones. So temperature control can be challenging. You can imagine that it can be hard to pack these things with the catalyst. It can also be hard to unpack them when your catalyst lifetime is up. And because we're now packing this thing, it can be possible that you require high pressure drop to drive the fluid through the reactor. And so lastly, if we apply our general mole balance to PBRs, in minus out plus generation equals accumulation. It's going to look similar to the PFR. Okay, but again, we're going to be working in terms of catalyst weight and a differential catalyst weight, not a differential catalyst or reactor volume. We're at steady state, so our accumulation term goes away. And if we make similar assumptions as before, we can get our ideal PBR design equation, or dF dW is equal to Rj. So with that, we have now derived the general mole balance equations, or our design equations, for 4 main and major reactor types that we're going to be talking about in this class, starting with just a general reaction of A goes to B. Okay. And we can rewrite these, for our non-steady state ones. We can write them in their differential form. Of course, we can also solve them in their integral form by applying the initial conditions and predict, for example, how concentration or number of moles of our reactor species is changing over time, or volume or weight within our reactor. And for our algebraic one, we have our design equation for our CSTR. So again, our equations can be either differential or algebraic in nature. And next, we'll be talking about how to apply these to the design of different reactors after we start to make a few more less simplifying assumptions. In this next video, we're moving on to chapter 2 in our Fogler textbook, and we'll be talking about conversion and reactor sizing. So we'll be defining what conversion means. We'll then be rewriting our general mole balance equations in terms of conversion. We'll talk about how we can use conversion to aid in reactor sizing, figure out how big our reactor needs to be, comparing our 2 continuous flow reactors, CSTRs and PFRs, to see what things look like in terms of relative sizes to achieve, say, a similar conversion. And then we'll be looking at reactors in series and see what benefits that can have with respect to the overall design. So conversion from here on out will be denoting as X, and it's a parameter that's going to be very useful for simplifying our reactions, as well as for defining specific targets in terms of how far we want our reaction to proceed. We always define it with respect to one of our substrates, especially if we have multiple reactants, rather, in our reaction. And ideally, what we want to use is our limiting reactant. Limiting reactant is, of course, the one reactant that you would run out of first. Okay. So to aid in this, normally we would take our balanced relationship and normalize our stoichiometric coefficients with respect to our limiting reactant, such that its coefficient is 1. So if you look at the reaction, generic reactions that's shown, if A is our limiting reactant, we divide by lowercase a, our stoichiometric coefficient for A, and then that normalizes each of our other coefficients. And conversion will be defining, again, as X, in this case, X sub A, our limiting species. And we'll be referring to a conversion as the moles of A, in this case, that are reacted versus the moles of A that are fed. And so what do we mean by fed? Well, if we're talking about a batch system, the moles fed are the amount of moles of A that are there at the start of the reactor, i.e. how much we put in. And if we're talking about a continuous flow system, the moles of A fed is going to be the amount that are entering the reactor in our feed stream that's continuously flowing in. So then, using that definition for our batch reactor, We can then define it with respect to the total moles in our system. So if we have moles of A remaining, N sub A, that's going to be equal to however many moles we initially had, N sub A naught, minus however many moles reacted, N sub A naught times X. So that any time in our reactor, if we want to know how many moles of A we have remaining, we could calculate that as the initial moles fed times 1 minus X. So using that relationship, then we can return to our general mole balance for our batch reactor, which we see on the left-hand side. And again, we're talking about moles consumed in this case of one of our reactants. So we want to be careful with our negative sign. We can then use the definition of our conversion equation, okay, and solve for that, take the derivative of that to get a relationship that relates the change in moles of A versus the change in conversion. And then from there, we can combine those and get a new relationship for our general mole balance equation in terms now of conversion. Okay, so this will allow us to determine how large of a volume we need to achieve a certain conversion in a certain amount of time. Now, we can also use that and separate and integrate, and we can determine, probably the more useful way we'll use this equation is to determine how much time it takes to achieve a certain conversion. Now, if we're talking about a flow reactor, again, we're focusing not on the moles that are added, but the moles that are entering and leaving our system. So by a similar approach, we can come up with a relationship to determine the flow rate of A leaving the system relative to how fast it's coming into the system relative to our conversion. Likewise, we can take a look at our design equation first for our CSTR, one of our flow reactors. We see our general mole balance on the left-hand side. We now have our conversion equation there on the right-hand side, which we just introduced. We can use that to substitute for F sub A, go through some simplifications, and again, now rewrite our design equation for the CSTR in terms of conversion. Okay, so we can use this equation to determine the volume of the CSTR needed to achieve a desired conversion, among other things. For the PFR, our other type of flow reactor, we can take a similar approach. In this case, we have DFA, DV, DRA. We have our conversion equation here, same as before. We now want to replace DFA so we can differentiate both sides and relate DFA to DX. We can then substitute that in, and ultimately what we see is that we can rewrite our integrated form of our general mole balance for a PFR to determine through integration the volume of the PFR required to achieve, again, a desired level of conversion. Same basic approach we would take for the PBR, and we get an analogous result now in terms of catalyst weight instead of reactor volume. So in summary, here's what we had before of our general mole balance equations in terms of moles of reactant A, for example, or species A, and their changes. And now if we rewrite that, we can cast our design equations for our batch, CSTR, PFR, and PBR instead in terms of conversion. And in this case, as numbers of moles goes down as a reaction proceeds. In this case, for example, if we look at the batch reactor, as the moles are going down over time, our conversion is going up. Ultimately, it's going to approach its maximum value of 1. So we said that one thing that we can use these relationships for is to determine the size of a reactor that would be necessary to achieve a certain performance criteria, such as a certain level of conversion. And we can do this, for example, with a CSTR, if we know how our reaction rate depends on conversion. This is something usually we know or we can determine using our definition of our reaction rate or our rate law, as well as our definition of conversion. Okay, so we can see that as our conversion changes, it's going to be increasing. Our reaction rate should be changing as well. Okay. And in fact, as our conversion increases, concentrations will be getting lower. We should expect that our reaction rate will be decreasing. And so here, the question is, what happens to the reaction rate as we get closer and closer to perfect conversion? As x goes to 1, concentration of our reactant will be going towards 0, so we expect that our reaction rate will be slowing down, approaching 0 as well. Well, what happens in that case if we have a CSTR as our reaction rate approaches 0? That means our volume will be approaching infinity as we divide by 0. Okay, so full conversion or maximum conversion in this case would be something we would like to approach, but it may not be feasible to actually achieve full conversion in a flow reactor, including in a CSTR. But what we can do is determine the volume that we would need to achieve a specific conversion less than 1. Again, if we know how our reaction rate depends on x. So if we consider our ideal CSTR design equation, another way we could write this is the product of this ratio, Fe naught over Ra, times x, our conversion. And so if we were to plot that function, it would look, perhaps like this for our reaction. Then we could calculate the volume of the CSTR simply as the area, so the length or the height times the width of this rectangle or square here, as determined by our target conversion. So this type of approach we call our Levenspiel plot, as is named after a chemical engineer, Octave Levenspiel. So let's look at an example and see if this makes a bit more sense. So here we have some experimental data, for example, that shows how Fe naught over negative Ra is changing as a function of conversion. Okay, we can see that as conversion is increasing, so too is this value, most likely because our reaction rate is decreasing as our reactants are being consumed. So if we took this data and created our Levenspiel plot, then we could ask the question, what would the volume of CSTR be needed to achieve a conversion of 0.4 or 40%? And then likewise, what would be needed to achieve a conversion of 0.8? Well, in the case of 0.4, we can see that we could draw a rectangle here from 0.4, and we can read off the value of Fe naught over negative Ra. So 0.4 times 2, that would give us a volume of 0.8. Whereas if we wanted to achieve a conversion of 0.8, now twice the conversion, we see that the total volume required to do that would be 8 times 0.8 or 6.4. So several times greater than the volume to achieve twice the conversion, about 8 times. We can do the same type of approach using the 11 Spiel plots to also size PFRs, i.e. determine what volume of PFR we would need to achieve a specific conversion or target conversion. Here's our ideal PFR design equation. And we, from what we know about integrals, if we were then to plot FA naught RA versus X, okay, this value is equal to the area under the curve of our function, FA naught over RA versus X. So if I were to create that plot, rather than creating a rectangle as a product of our length of our x-axis and our y-axis, now our area under the curve is what's equal to the volume of the PFR. So let's return to the same data set and ask the question, what volume of PFR would be required to achieve a conversion of 0.4? Well, in this case, we'd be taking the area under the curve from 0 to 0.4. We can always see that's going to be less than, okay, by a little more than half of what it would have been for the CSTR. Now here we'll have to use a numerical integrator, so something like MATLAB, or you can do this in Excel. Or you can do it by hand using, say, something like the Simpson's 1/3 rule. And we could estimate now that the volume of the PFR to achieve a conversion of 0.4 in this case would be 0.55. Notice that this is less than, not a little bit more than half, again, of the volume that was required of the CSTR to achieve the same conversion. So generally, when our kinetics follow this type of relationship, we can see that the volume of the PFR is going to be less than that of the CSTR. Now, so far, we've been talking about individual reactors, be they a CSTR or PFR, specifically focusing on flow reactors here. But sometimes, and we'll talk about why it can be useful, sometimes we may be beneficial to have multiple reactors in series. That can be a CSTR followed by a PFR, and a CSTR, or multiple CSTRs in series, or even multiple PFRs in series. We'll see which ones make the most sense. In this case, we can still use conversion to aid us in the design process. In this case, we want to think about conversion in a slightly different way. We can think about it as the conversion out of one of our reactors, as well as the subsequent one, and then as well as overall. Okay, so we'll define our conversion now as x sub I, conversion up to a point I, say where I is 1 after the first reactor, or 2 after the second reactor. That'll be equal to the total moles of A reacted up to point I over the total moles of A fed to the first reactor. So going all the way back to the first reactor. So if we're comparing then what's coming out of our second reactor, we'll relate that not to what comes into the second reactor, but what comes into the very first reactor. So always with respect to FA naught in the original feed stream. So with that, let's think about CSTRs in series. So in this case, we have one CSTR, and the effluent of that becomes the feed to a second CSTR, and then overall we'll achieve a conversion of X2. Here's our general mole balance for our first CSTR. We have our conversion equation. We can first then substitute this in to eliminate FA sub 1, the flow rate of A coming out of reactor 1. And as we rearrange that, we can then write and determine the volume of our first CSTR required to achieve a conversion of X1. Now, what about CSTR2? Now we have our general mole balance. In this case, what's coming in is what's leaving the first reactor. And we're going to substitute in for our conversion equation. In this case, again, it relates to what's initially coming in the original feed stream. We can substitute that in to eliminate for Fa sub 2. And we also need to substitute in for Fa1. And after we do both of those things, we can then write a design equation for CSTR2, which says that the volume required is equal to Fa naught over negative Ra at the rate of reaction in reactor 2 times the difference in conversion coming out of reactor 2 versus what was coming into reactor 2 or coming out of reactor 1. So we may ask a question, why would it be useful to use two CSTRs in series instead of just a single CSTR? And again, it can be helpful to look at our Levenspiel plots to answer that question. So let's consider the case where we have our two CSTRs in series, and let's consider, for example, in our first CSTR, we can achieve a conversion of 0.4, but we are interested in achieving overall a conversion of 0.8. We can see that the area under the curve, now we would be wanting to consider the total area. So we would have our 0.8 meters cubed of our first CSTR. Then this would give us additional 3.2 meters cubed for our second CSTR. Overall, we would need a total volume of 4 meters cubed. And if instead we wanted to achieve the same total conversion of 0.8 using a single reactor, well, we can see by comparing the areas that the total volume would again be 6.4 meter cubed as we saw before. So typically, what we see is that if we want to achieve the same overall conversion, then the total volume of CSTRs in series will be less than that of a single CSTR. In other words, we can achieve the same conversion using a series of smaller CSTRs than we could using a single very large CSTR. Now, what about PFRs in series? We said a PFR effectively, the volumes related to the area under the curve of Fa naught over negative Ra by Xa. And so consider the case where we have 3 PFRs in series versus a single large one. In this case, the three PFRs in series, the areas would be additive, and we see that would add up to the total volume of the single PFR. And hopefully that makes sense, as PFRs are essentially tubes, and if we have 3 smaller tubes versus 1 larger tube, it's just like we're connecting the outlets of those tubes themselves. Now, the other scenario we might consider is having CSTRs or PFRs in series, and we can see that the configuration of that is important, and it can be used to our advantage to reduce the total volume of our process, and that's going to reduce the cost of our process. So say, for example, we had a CSTR followed by a PFR. In order to achieve a conversion of 0.8, that would give us a lower total volume of reactors than the opposite scenario, using a PFR followed by a CSTR. So a couple more definitions that are going to be useful going forward. In addition to conversion, another parameter we like to consider is space-time. And we calculate space-time, we call it tau, as the ratio of the volume of the reactor over the entering volumetric flow rate. So it's a way of normalizing our process to make it somewhat scale agnostic. And if we think about what space-time means, that ratio, it's also sometimes referred to as the mean residence time. It's equal to the mean time that a particle would spend in a reactor, okay, between when it enters the reactor and when it leaves. This would be the average amount of time that a typical particle would spend in that reactor. We can also talk about the space velocity. This is the inverse of the space time. Okay? And it gives us a sense of how fast the particle is flowing throughout the reactor. So we'll be using these two parameters later in the course. Okay, moving on to chapter 3, our focus is on rate laws. We're learning how to relate rates of reaction to each other through the rate law relationships, writing rate laws in terms of concentrations, and then using the Arrhenius equation to find rate constants as a function of temperature. So in a chemical reaction, what we typically see is that the rate of reaction is going to increase as the concentration of our reactants increases, and that's because the frequency of molecular collisions between reactants will increase. The particles or molecules rather are closer together. And increasing temperature has a similar effect as the kinetic energy of those molecules increases. They're moving faster and colliding more frequently. So therefore, we would expect that the rate of reaction usually is a function of both concentration and temperature. Our rate law will capture how concentrations of our reactants affects the reaction rate. And it's our rate constant, meanwhile, that's going to capture how our reaction rate is a function of temperature. Usually, we can model the dependency of a rate constant on temperature. There is a strong dependency there using the Arrhenius equation. The Arrhenius equation here shown on the left. The main parameters are the pre-exponential factor and the activation energy. We also use the ideal gas constant. And an important thing here is we want to be using absolute temperature, i.e. in units of Kelvin. So typically what we see, if we go to a temperature of absolute 0 Kelvin, there'll be no kinetic energy for our molecules. There'll be no collisions. We'll have no reaction rate constant, no reaction taking place. But as temperature approached infinity, then our value of K would approach the value of A, the pre-exponential factor. So you can see a cartoon depiction of how our rate constant might vary as a function of temperature, and it's a strongly nonlinear function. The activation energy, again, along with the pre-exponential factor, is those are the two main parameters that we need to model the temperature dependence on the rate constant. And we determine both these experimentally. And so, for example, we can run our reaction at several different temperatures, estimate our rates and our rate constants, and then linearize our Arrhenius equation, such as ln K versus 1 over T, and a slope of those data would be equal to the negative of the activation energy over R, whereas the y-intercept would be equal to ln, or the natural log of the pre-exponential factor. So that's how we can capture the effect of temperature. Now, what about concentration? Typically, what we see is that our reaction rates will follow a power law model. So if we have reaction of A plus B goes to C, we have two reactants. The stoichiometric coefficient of the in an elementary reaction, rather, the stoichiometric coefficient of the species would be equal to the order of that reactant, but that's not always the case. So in this case, more generally speaking, we could write our rate law according to the power law model, where it would be K times Ca to the alpha, that's the order with respect to A, and Cb to the power of beta, the order with respect to B, where the overall reaction order is the sum of our two species orders. If we had a zeroth order reaction, there would be no concentration dependence. If it were first order, for example, only with respect to one species, so say our reaction was just A goes to B, then it would look something like this. Second order, it would depend on that concentration squared, and third order cubed, and so on and so forth. In general, determining the order is something that we need to do experimentally. Okay, we don't always want to assume that it's an elementary reaction. We want to determine the order experimentally so that we know we're accurately representing the dependence on concentration. However, I mentioned elementary reaction previously. If we have an elementary reaction, and this is often the case if our reaction involves just one step, so not an intermediate step, and the stoichiometric coefficients are identical to the powers in the rate law. And so, for example, if we had the reaction of 1A plus 2B goes to 2C, and we were able to model our reaction rate as K times Ca to the power of 1, Cb to the power of 2, i.e. second order with respect to B, and first order with respect to A, we would call this an elementary reaction. But again, this is not always the case and not something we necessarily want to assume. We want to use experimental data to inform what the reaction rate law is. Now, sometimes we can have reversible reactions. These are reactions that will not proceed to, say, 100% conversion. They'll proceed until reaching an equilibrium. At the equilibrium, our rate of our forward reaction is equal to our rate of our reverse reaction, in which case we can determine an equilibrium constant as the ratio of our forward to reverse rate constants. In this case, whereas temperature can influence both rate constants, we typically capture that as its influence on the equilibrium constant. So now moving forward to chapter 4, where the topic is stoichiometry, we'll be learning how to relate concentration with conversion for batch and flow systems, and writing a reaction rate as a function of conversion so that we can calculate equilibrium conversion for batch and flow systems, i.e. learning how we can derive an equation to model our reaction rate as a function of conversion. So the main steps that we'll be taking in order to find out how our reaction rate varies as a function of conversion will be to first relate all of our individual species reaction rates to their concentrations. We already have seen examples of how to do this. We use the number of moles of each species in terms of their, we'll change the number of moles of each species in terms of their, and rewrite those in terms of the limiting reactant. In this case, A, we're going to assume is our limiting reactant. We'll then relate all of our species concentrations to volume or volumetric flow rate, depending if we have a batch or a flow system. And then we'll relate volume or volumetric flow rate to our conversion of our limiting species and put everything together to get that final function to relate the reaction rate of our limiting species with the conversion of that species. So how do we put the number of moles of each species in terms of our limiting reagent? Well, we take our stoichiometric coefficients and normalize by that our limiting reagent. So if A is our limiting reagent, we can normalize all the coefficients with respect to A. It has a similar effect on relating the rates of consumption or depletion of our species as well. And so we're doing this now to reduce the total number of unknowns in our system. So what's important here is to remember that just because we can write our conversion with respect to our limiting species, that doesn't necessarily mean for every mole of A that's consumed, we consume equal moles of B. It depends on the stoichiometry between A and B. Okay, so conversion in this case is always written with respect to our limiting reactant. So using these ideas, normalizing with respect to stoichiometry, we can prepare a stoichiometric table to keep track of what's happening to each of our species in a batch process initially and over time up until some conversion. So for example, for species A, we initially start with N sub A naught. If we run our reaction for a certain amount of time to achieve a conversion X, we will have converted away N A naught times X, and we'll have remaining Na equal to the difference between what we started with and what was reacted. B will be reacting away as one of our substrates as well, according to its stoichiometry relative to A. So for example, if the stoichiometric coefficients were equal, we would see equal parts of B being consumed. But if they're not equal, then that's not the case. They would be consumed in proportion as determined by the stoichiometry. So that's how this is helpful. Likewise, we can track how much of C gets made relative to A being consumed and how much D gets produced relative to A being consumed. Now we can introduce a couple of parameters to help simplify this a little bit further. Delta can be the sum of each of our stoichiometric ratios. And this relates to the total change or change in the total number of moles per mole of A reacted. And then we can also introduce theta. We can have a theta defined per each species. There's theta sub I. This is the ratio of initial moles related to A. So how many initial moles of species I we have relative to species A, because those may not be equal as well. We may typically we'll be adding more of one species than another. In this case, A is going to be our limiting species. It will have the least number of moles initially, depending on the stoichiometry. So using that definition of theta, we can now also rewrite our initial mole equations for each of our species, as well as use that to determine how many moles are remaining. Okay. And ultimately, why we're doing this is we want to be able to relate the concentrations of each of our species with respect to the conversion of our limiting species. Okay, and so now we can recast our expressions here. This one remains unchanged, but we can now rewrite equations for CB, CC, so the other reactants and products of our reaction with respect to the conversion of our limiting species. And the purpose of this is so that we can now rewrite our rate law with respect to conversion of our limiting species. So we can substitute in for Ca, concentration of our limiting species, or Cb, concentration of our other reactant, and now we can get a single expression for the rate of consumption of our limiting species with respect to conversion of that species and some other stoichiometric relationships and other ratios of initial concentrations. So now we have our rate of reaction in terms of conversion, and we can use that plug that into some of our ideal design equations that we were introduced to in Chapter 2.